Welcome back. Today we'll be talking about the Baldwin-Barth turbulence model, some of its motivation, formulation, and the original validation results. The model, which is one of the most popular and original first equation models, inspired the Spalart model, Spalart-Allmarus model, that is, and the Mentor's two-equation model. They were both reviewers of this original paper while they were at NASA Ames. Here's the original document, one equation turbulence model for high Reynolds number well-bounded flows by Barrett S. Baldwin and Tim Barth. And we'll look at this particular document after we go through the notes, which is available on the NASA Technical Report Server, or ntrs.nasa.gov. And I talked to Dr. Tim Barth via email, and he was very kind to provide this personal photo and a biography and a little bit of history in a statement. So let's go through those together. He was educated at University of Minnesota and got his master's and Ph.D. at Stanford. And at the time of the recording, he's still a research scientist at NASA Ames Research Center in the supercomputing division. And he won a number of excellent awards. The Lawrence Sperry Award, which is usually given to younger researchers in the beginning of their career, a medal for exceptional scientific achievement from NASA, and he's currently on a number of editorial boards, and his current research interests are still the same, CFD and numerical methods for partial differential equations. That was a personal correspondence. And this statement here was written to me in an email by Timothy Barth, and he wrote that Barrett had a long history of working on turbulence models. The model Cebeci-Smith was being used in boundary layer calculations, but it became clear that it was not very compatible with general finite difference methods being developed for the Rand's equations. So Barrett and Lomax developed the Baldwin-Lomax model for CFD, which essentially reproduces the Cebeci-Smith estimates for boundary layers, but also handles crudely more general flows encountered in Rand CFD, e.g. separation. Much later, I began talking to Barrett about the lack of robustness associated with two-equation K-epsilon models advocated at the time: excessive stiffness, poor stability, non-physical negative viscosities, etc. Unfortunately, the two-equation nonlinear systems with source terms are difficult to analyze, although a theory for 2x2 hyperbolic systems does exist. Without a good understanding at the PD level, it is nearly impossible to design numerical methods that guarantee stability and non-negative viscosities. Fortunately, I did understand the theory for one equation infection diffusion source term PDEs and techniques for constructing numerical solutions that inherit those PDE properties. Purely for the reason that we could analyze and understand one equation PDEs, we set out developing the one equation Baldwin-Barth model, which is the subject of this talk. After writing a manuscript on the one equation model, we gave the manuscript to Philip Spalart, then at NASA Ames, and postdoc Florian Mentor, and they reviewed the papers, which is how NASA works today. When you write a paper in NASA, it's reviewed by others before sent out for publication. Philippe left NASA Ames to join Boeing, where he developed his own one-equation model, and Florian went on to develop a robust two-equation model that blends K-omega and the K-epsilon model. Both models address robustness when used in Rand's calculations, and that was written by Tim Barth in correspondence to me via email in this year, 2022. So let's look at some introductory notes and about this model. I've already mentioned some of these you can allude to from what I just read. It did emerge from NASA Ames Research Center. You can see a theme. A lot of these great RANDS models used throughout industry today are. And it's a one-equation model that avoids the need for an algebraic length scale, which is derived from a simplified form of the K-epsilon equations. I should mention they're trying to form a new equation for some turbulent Reynolds number. After calibration on the model on well-established properties of the flow over a flat plate, predictions of several other flows are comparative experiment. So the calibration is for flat plates and run on other flows. And the one equation model is analyzed numerically for robustness. Let's talk a little bit about the motivation, which I just mentioned, and you saw directly from Tim Barth. One motivation, of course, was for the developments where well-established models would have an inability, with algebraic solvers at least, in closure, to predict severely separated turbulent flows. And in particular, these were identified in the Viscous Transonic Airfoil workshop, which you can still read about today. You can go online and find the proceedings. And in these flows, these transonic flows contain separated flows, and they were bad results, or bad, or maybe poor results all around, including the algebraic model of Baldwin-Lomax, which we already talked about in this class. So I'll write poor results from algebraic models. And there's many cases that were looked at, including Johnson and King, Coakley, and other researchers that showed similar bad behavior. And one thing that came out of the workshop was a need to avoid algebraic length scales. And so one-equation models are the next logical step. Now, they thought it was worthwhile to investigate the possibility of transforming their variables from, say, a Kaplan model to some basic one variable where they understand the numerical behavior of a simplified equation relative to more complicated Kaplan equations. So they sought, or they will seek, a consistent one equation model that avoids algebraic length scales. And you saw in our earlier development, algebraic length scales are pretty important for model formulation. And they wanted to present this model and show the application to a range of difficult problems, so it's robust. And they wanted to overcome the problems identified in the Viscous Transonic Airfoil workshop and report their work. Overcome problems in Viscous Transonic workshop. So let's look at the derivation of their model. They started with the standard K-epsilon model. Oops, I wanted to highlight that, excuse me. And here is the K equation, so that's the turbulent kinetic energy equation for K. And the dissipation equation, where the dissipation of turbulent kinetic energy is epsilon. And later in this class, we talk about some famous two-equation models like K-epsilon-Landau-Schar model. Here, if you don't recall, d dt is the total derivative defined here, and P is production of turbulent kinetic energy, and epsilon is defined next. So let's look at some notes about this equations. We want to form a third equation from these two equations. And it should be an equivalent system. And we're completely free to do any nonlinear or linear combination of these two particular equations. And it'd be a new field variable, And what that field might be is a turbulence Reynolds number. And turbulence Reynolds number isn't a new concept to them or in modeling, but this is the variable they chose to seek. And here, turbulent Reynolds number would be something like turbulent energy squared, kinetic energy squared, divided by viscosity divided by dissipation. The turbulent Reynolds number goes as turbulent kinetic energy squared divided by viscous energy and dissipation. So somehow we need to form RT from our K epsilon equations. And we might do that by looking at the differentials RT, dRT divided by RT, which would go as 2 times dk over K minus d epsilon over epsilon. So it should be clear that that total or material derivative of K and epsilon could be transformed in some form like this to make a transport equation for RT. So if we transform the diffusion terms, which are modeled in both K and epsilon equations, we can omit particular terms, which are noted in their paper, from the transformation to obtain a new diffusion model for the turbulent Reynolds number RT. And that's what this equation is here. And you can see now there's this eddy viscosity nu T, for instance, in this term. And that would go as C mu, which is a constant, times nu RT. And so our transport term is a viscosity times the turbulent Reynolds number. And we have an eddy viscosity, which we can track in the momentum equation of the RANS equations, Reynolds average, Navier-Stokes. A quick note, since nu T, the eddy viscosity, is not dependent on nu at large RT. And therefore, the appropriate field variable is nu RT equals K squared over epsilon. So that checks out, rather than just RT. Now we can take equation 518 for turbulence Reynolds number, and we can rearrange it in the form for epsilon, the dissipation turbulent kinetic energy right here. So that's just rearrangement of 5.18. And we can write it as K1 plus K2 squared. So we're just taking K and summing it as K1 plus K2. And we can rewrite it, so we recover the same equation as K1 squared equals nu times RT times production. Notice P is production. And second, for K2, the production minus nu RT P root. And you can see if we add the two, we obtain the original definition. So now we have a two-layer model. I think that's the motivation for this. In regions where K2 is less than K1, we'll get something like production goes as dissipation, meaning it's in equilibrium. And we'll have this new relation where we square the K and substitute definitions for K2 and K1 and expand. We'll get this form. We'll get nu RTP times 1 plus K2 over K1 squared divided by nu RT. And therefore, using this definition, we can square both sides, K squared, or square root both sides, K squared, and the right-hand side of 524 and get 525. And we get K as the root of nu RT times production times 1 plus K2 over K1 in simplicity. So we haven't done anything, we just split it up. And now we can take equation 523 right here, K2, and substitute it in 519, which is our transport equation. And we'll get a modified transport equation where we have it in terms of K1 and K2 and nu RT. We still need to close this system, and we can take equation 523, which is our K2 equation, and substitute it in 523, and substitute in the K equation, original K equation, which is way up here, 516. And we'll obtain this modified K equation. So we slightly simplified the K equation based on two-layer model using RT as our one equation PDE. So we have our transport equation, which is 526, And let's apply it and see what happens to wall-bounded flows. We'll neglect the last two terms in 526 for wall-bounded flows. Here, oops, here and here. We'll find a self-consistent one-equation model that should be valid over a major range for sheared flows. And for that purpose, all the previous relations will be taken to be applicable at large RT. Meaning large turbulent Reynolds number, and focus on sheared flows, which are for boundary layers. So for near wall regions, we would note that the Reynolds number can be split into two factors, and we might write that as RT tilde times a function F3, which we'll introduce, and RT tilde function. So F3 is a function RT tilde and RT. And F3 is a damping function where RT goes as RT tilde for a large turbulent Reynolds number, meaning we're away from the wall. Near the wall, we want RT to become small. This damping function is used in many K epsilon models at the time, and that's what inspired it. And here they'll rewrite eddy viscosity as the viscosity times the coefficient C mu times this function F mu times RAT, and substituting RE tilde, we have this one for F3. So the difference is F3 times RE tilde, and we have a new form of dissipation we'll call epsilon prime, which will be epsilon minus the destruction term, goes as k squared over nu RT times K1 plus, which is K1 if we substitute K1 to K2. So for K1, it's small RRT, and therefore RLT would be reduced to this form here. And we would like K1 to be the dominant part of K in the near wall region if that damping function is designed properly. So the new field equation will be for RT tilde, as you can see right here. And we've taken these properties for eddy viscosity and K1 and substitute in this equation of 532. If our flow is incompressible and there's no pressure gradient, then we can try and design a damping function. And once we do that, we would let it be applied to flows which are compressible and with pressure gradients. But that's how we're going to sort of design or determine this particular damping function for model calibration. And to do this, they make the thin shear layer approximation so that the production is approximately the following. Nu t times uy squared. That's partial u, partial y squared. And that's the thin layer assumption. If we make this assumption, then our model equation will reduce to 534. And our transport term reduces to 535. So you can see we've made a slight simplification for our incompressible zero pressure gradient flows. And you'll note that for, say, high momentum thickness boundary layer, what will happen? The Reynolds number will begin in the log layer and it'll occur in a region where the total shear stress is approximately constant and equal to the shear stress at the wall. All right, total shear approximately constant and equal to shear at the wall. In the longer region and below, that's the viscous sublayer, where advection terms are negligible. The x-moment equation will simply become nu plus nu t, that's the viscosity plus eddy viscosity, times partial u partial y, will equal to that wall shear stress squared. Excuse me, friction velocity. What am I thinking? So Utah is defined actually as the shear stress at the wall divided by the density of the wall, incompressible. Now in the log region, partial u partial y goes as ut over ky, which is log law of the wall. And the eddy viscosity is much larger in that region, and eddy viscosity in that region might go as nu times cu RT. Then eddy viscosity in that particular region goes as the friction velocity squared divided by partial u partial y, which will be reduced to k ta over y. There. K is on the order of 0.41 as normal, and therefore RT up here will be reduced to nu t over nu cu, which upon substitution, get a different color, gold, right there, will go as k over c mu times uty over nu. In this case, the turbulent Reynolds number, the second derivative of it in the cross-gene direction in the boundary layer, and substitution of 535, which is this equation, with a particular damping function set to unity, the advection terms will be 0 and produces the following simplified equation for closure. Now, in regions below the log layer, an additional relation is required to determine the definitions of RT and F3 as a function of RT. And in a study which is more detailed in the paper and the analysis here, they propose in the log region and below, including the viscous sublayer, that RT tilde goes as k over c mu times friction velocity times the distance to the wall y divided by the viscosity. And this relation here, 540, can be consistent with the field equations by requiring that the damping function F2y plus can be adjusted to accomplish the purpose. So they need to adjust that damping function so that 540 is true. And through this procedure, they have determined the following damping coefficients, which we saw earlier in our equations, F mu and F3, goes as d1 over d3 and d2 over d3, and they define d1, d2, and d3 as these exponential functions. The first one here looks very familiar to us from previous models as 1 minus e to the negative y plus over a plus, where a plus is 26. That's Van Dries. The others are combinations, which are done by calibration against the incompressible flow. Let's make a few notes about these. And remember, y plus is defined as friction velocity times distance to the wall divided by viscosity. And F mu times F3 goes as d1, d2, based on these definitions of 541 with 542. So we note that neither F mu nor F3 is equal to d1 or d2. And we see that if we implement this one equation model, it'll only require the evaluation of the product of F3, or excuse me, F mu times F3. This should be F3. And finally, d1 and d2 are just simpler functions than F mu and F3. And so we might be able to replace in a model implementation the product of F mu F3 with d1, d2 wherever it occurs. So that might be something like 1 over closure coefficient, oops, RE ta tilde equals Prandtl constant divided by C mu, closure coefficient, times Utah y over mu. So if we take equation 539 and 540 in equation 535 with d RT tilde dt is 0, we'll get this equation 543. And substitution of 536, which is something like nu plus nu t uy equals Utah squared. In equation 529 and 540, we can get this function for f2y plus. And for small values, if we take the limit of 544, we need to find this closure function. And as y goes to the wall, it'll be reduced to this particular equation. So this means that after the assignment of these parameters, C epsilon 1, C epsilon 2, kappa, we can use and determine the particular damping functions for F2 y plus. When combinations of F mu and F3 equals D1, D2 is known as a function of y plus. So the constants chosen at the wall by Baldwin-Barth are F2, 0 equals 0.781. Now equation 540, way up here in the log region, it can be seen that y plus is indeed a damping function, and it should be replaced by this form when the pressure gradient is 0. Now, for general flows that involve non-zero pressure gradients, the dependent RT or y plus is not interchangeable. And they will try and find which function they would like to use through practice and computations. And they try to have their model depend on y plus distance, but that's probably not the best final choice. And in later models, they try to relax this, maybe restriction in their model. And they've calibrated their functions with comparisons with the Cebeci-Smith model using equation 5.36. I'll just make a note that they relax their use of y plus distance in later papers and publications, but we're just looking at the publications. We're just looking at the major formulation of their model. So let's look at the final summary of their model, just to see in its full form. Remember, it's a one-equation model of Baldwin and Barth. They have an eddy viscosity defined as a coefficient times the viscosity times turbulent Reynolds number times that D1, D2 function which we described. And they have a single equation, that's why it's a one-equation model for turbulent Reynolds number, eddy viscosity times their turbulent Reynolds number. And here we show all their closure coefficients, which we talked about. These are constants. This is a very typical one. This is the one of Van Driest. This is theirs. And they have D1 and D2, which appears right up here in their model for eddy viscosity. They have their production and other closure coefficients. This is damping. And they have some final notes on this. Well, let's just leave this here where we note them. We note that it's a complete model. It actually involves no adjustable functions or coefficients, and it's calibrated based on the log law of the wall for incompressible flow with zero pressure gradient. That doesn't mean it's suitable for other applications, but we calibrated it that way, and now we're going to apply it to more difficult flows of separation, high pressure gradients, and compressibility. And it constitutes, perhaps, what they argue as the simplest model enclosure for turbulence by taking a two-equation model and putting it into a form of one-equation model for turbulent Reynolds number. And in particular, it circumvents the need to specify a dissipation length, like in previous models, or some length scale like L, as we saw in previous equations. And this means that in this closure, epsilon v would be 0 when spatial gradients are vanishing. Now let's look at their paper itself, which I have right here. I'm going to go up to the top. So there's Baldwin-Barth, published in 1990, August. One equation model for high Reynolds number flows out of NASA Ames. And you can pull this paper yourself by going ntrs.nasa, NSA, that's a different site. Gov. And just go ahead and type in, you can type in the title or just search for Baldwin-Barth in 1990 and it should come up. And like all good papers, it's a summary, but we've talked about this formulation. If you want more mathematical details, you can go into this paper yourself. But I want to look at their most important results for viscous transonic airfoils. Let's go do that. And they looked at two major cases. Here's the first, RAE 2822 airfoil. So there's their mesh. Flow goes left to right. And we should expect at this high Mach number, I think Mach 0.75, you'll see something like a shock wave appear. And there'll be separation in this region. Now, let's look at contours of Mach number, where m infinity equals 0.75. So each of these lines here is a constant Mach number. And on their figure, they don't have a contour legend, but you can see right here is their attached shock wave on the suction side of the airfoil, and this region here is separation, and that's what their prediction looks like. So that's a nice qualitative prediction, but let's see the quantitative results compared to experiment and past models for RAE 2822, and they predicted C sub P. So this is x over c, that's the axial position on the airfoil surface divided by the chord from the leading edge to the trailing edge. So the airfoil looks like this. And here is the shock. Y-axis is C sub p, meaning pressure coefficient. It's always plotted in the negative direction in aerospace engineering, so always watch for that. Here's the zero value. The lower lines are the pressure side, and the upper lines are the suction side. And here the experiments are circles. The one equation model is the one we just developed or looked at its development, and the dotted lines are the Baldwin-Lomax model. So on the pressure side down here, all the results agree really well, which is great. There's no separation, there's no shock, but on the upper surface the shock forms. And in this case, the experiments and the new one equation model agree pretty well. In fact, the shock is predicted a little bit downstream than where it was in experiments, but remember, experiments aren't perfect, and these shock waves, since they're transonic, are actually vibrating back and forth really quickly, so they're not really stationary. And this dashed line is the prediction of the Baldwin-Lomax algebraic model, which we previously talked about in this class, which is about 0.1 chord downstream, 10% of a chord. That's huge. So you can see in this one case, they've shown superior prediction in terms of level and position of the shock. Let's look at one more case. This is the NACA 0012 airfoil. It means it's symmetric airfoil. It's 12% thick from the National Advisory Committee on Aeronautics. There's your airfoil and grid. Once again, a same type of flow should develop. We should see a shock in this location and separation here. Shock-induced separation, and the global Mach number is m infinity 0.8. That means way upstream in the left direction, your Mach number is at 0.80. M infinity means global, so that's be like the wind tunnel test section Mach number. Here we have Mach number contours again. See massive separation, adverse pressure gradient, and this is a normal shock here, and it's attached to the surface. Let's look at their predictions relative to measurement and other models. So here's again the pressure coefficient. Here's the leading edge of your airfoil, trailing edge. And this is here the pressure side and suction side of the results. The model, which was just developed by Baldwin-Barth, is here. Baldwin-Lomax is the algebraic model, and they also took their model and turned off the advection term just as a test to show how important advection term is in RAT tilde times viscosity transport model. You can see on the pressure side, there's actually a misprediction everywhere at about 0.2 chord, which is an issue. But more importantly, on the suction side, we'll have the shock wave correctly predicted in the full model relative to experiment, and the algebraic model and the new model without advection are way downstream at about another 0.2 chord lengths downstream. So you see they have solved the major problems of the viscous transonic airfoil workshop and showed that a transport equation of some type is important for shock separated flows or just separated flows with a strong gradient of pressure. You can check out the paper yourself and their formulation and even try out in your own codes. It's a famous model and it's not as used much today, but it did inspire the two models of Spalart-Allmarus and Florian Mentor, SST, which are the industrial workhorses today. So I think for that reason, it's really important to understand the motivation and formulation of one of the best closures of turbulence modeling. Thanks for your time.